Well, dear students, in this lecture, uh, I will discuss this application of kinetic theory. And the major application of this theory is this effusion to explain Graham's law. Basically, Graham's law is explained on the basis of this kinetic theory and mean free path, collision frequency, and this is very important to explain the reaction mechanism. So in future, when we study reaction mechanism, so in reaction mechanism, this collision theory, see wall collisions, right? This is very important. So here I am considering wall collision and effusion, diffusion and effusion or diffusion, right? So and the same concept is used to explain this reaction mechanism, how reactants combine and form the product. In that also this theory has great importance, right? So see, we we will try to study this concept basically in a very simple manner. Suppose that we have a container, right? We have a container and some gas molecules are there. So all of you are knowing that these gas molecules. So first we formulate the formula for collision uh, of gas molecules with the wall of the container, and then we will develop the concept for effusion and diffusion. So suppose that this molecule is striking with the wall of the container. Excuse me. So in a container, the collision is represented by Z. So Z with the wall is directly proportional to the area. In a very simple manner, if you specify certain area, suppose that we have specified this region, right? And some molecules are colliding with this area, specified area. This I have specified this length basically. If we double the area, obviously the number of molecules which are colliding with the wall, that are also double. So the wall collision of gas molecules is directly proportional to the area specified, right? Area is specified. And so first point is this, that collision 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 of gas molecules is directly proportional to area. No need to write here. I am writing in the mathematical term. Second factor, directly proportional to U average. See, this is the average speed of gas molecules. So if you increase the average speed, which can be increased by increasing the temperature. So I am not, we are not considering here the independent factor temperature, but in terms of this, we have two variables. One is temperature, another is molecular mass. So rather writing temperature and molecular mass, I am taking here U average. So indirectly I am taking temperature and molar mass both also. So if you increase the speed of gas molecules, obviously collision frequency or number of collisions increases with the wall. One more factor is there. That factor is ZW is directly proportional to N by V. Remember, dear students, what is this factor? N by V. N by V. What is N by V? N by V is the number density, right? Here it is more convenient when we are dealing at this level, molecular levels. So we prefer to use a number density rather than mass density. So N by V is the number density. Number density. Number density. So if you increase the number density, it means number of molecules. If you increase, obviously number of collisions increases. So basically the collision of gas molecules with the wall of the container depends on three main factors. One is the area specified, other is the average speed of gas molecules, and third one is the, because molecules with average speed we can say that this average speed is preferred term here to explain all these phenomena. So we can write here ZW means collision with the wall is equal to N by V number density into U average. Average we can write here. We don't write this because this will create some confusion. Average and what A. So one proportionality constant will come here, that is 1 by 4. 1 by 4, this is a constant, N by V U average. U, in place of U average you can write 8 RT by 8 RT by pi m 1 by 2 into A. So this is the formula of the collision with the wall of the container. If you analyze the unit of this right hand side, you will find the unit of ZW is per second. Unit of ZW is second inverse, also known as collision frequency. Collision frequency. Collision frequency, right? So this is called collision frequency, ZW, right? So ZW is equal to 1 by 4 N by V. This is very important formula, and from this formula we can derive, we can find Graham's law, we can define Graham's law. So basically Graham's law is based on the kinetic molecular theory, that is based on the molecular interpretation, that is not based on the bulk properties of matter, that is based on the molecular behavior of the matter, right? So this is at given temperature and for given gas, right? See this, if you take this, temperature is constant, gas is constant, so gas fixed for given gas, so all these terms are constant. So N by V number of molecules per unit volume. So obviously when we take container, volume of container is constant, because if for gases volume is the volume of container. So container volume is V and N are the number of gas molecules. A is the surface area or area is specified, right? Area is specified. So by using this equation you can calculate the collision frequency or collision rate. Collision frequency or collision rate. Collision rate. Right? Suppose that a question is given, example is given. Calculate ZW for O2 gas per second on 1 centimeter square of the surface containing surface of the vessel, right? If pressure is 1.0 10 to the power 6 atm, and and the temperature is 298 Kelvin, right? So see, calculate the ZW, right? Calculate the ZW. So I think all these things are visible to you. So question, yes. Now see, for ZW, we have to calculate ZW. So for ZW, first we have to evaluate N by V. So N by V is equal to, we can write here N A into N by Na is the Avogadro's constant, and are the number of moles by V. So in place of this N, we can put P by RT. So we can write here Na into P by right? So I think all of you are clear with this formula. How I have written this formula, N by V. I have written N is equal to number of molecules is equal to number of moles into Avogadro's number. I have used this equation, and number of moles N is equal to PV by RT. I have used this equation. So by using these two equations, I have written this. So on the basis of this information, because see here pressure is given, so we can evaluate this N by V. So N by V is equal to now Avogadro's number 6.022 into 10 to the power 23 per mole. Unit of this is per mole, and pressure is given 10 to the power 6 atm, 10 to the power minus 6 atm, right? Divided by what should be the value of R. You should take the value of R in which the unit will come atm. So 0.0821 liter atm per mole per degree Kelvin, multiplied by temperature 298 Kelvin. 298 Kelvin. So Kelvin, Kelvin cancel, atm, atm cancel, per mole cancel. So we will have this molecules per liter. So this is equal to 2.46 into 10 to the power 16 per liter. So this is equal to 2.46 into 10 to the power 19 meter to the power minus 3. So we have calculated N by V. Now A is equal to 1 centimeter square, 1 centimeter square. So this is equal to 10 to the power minus 4 meter square, right? And now U bar, you average 8 RT by pi m power 1 by 2. So this is equal to 8 into 8.314 joules per mole per degree Kelvin and 298 Kelvin divided by 3.14 multiplied by oxygen. So 32 into 10 to the power minus 3 kilograms per mole whole to the power 1 by 2, right? So on solving this, we will get 444 meter per second, right? Now ZW is equal to 1 by 4 N by V U average into A. So this is equal to 1 by 4 into 2.46 into 10 to the power 19 444 meter per second, and A is 10 power minus 4 meter square, right? So this meter square and this meter cube is cancelled, so we'll have per second, right? So 2.73 into 10 power 17 per second. So here you can write collision frequency or collision rate or collision frequency is equal to 2.73 into 10 to the power 17 per second. See, that is a huge rate of collision, right? And this collision will exert the pressure, and this is the main cause for the pressure of the gas, right? So hopefully all of you are clear. So see, this is the number of collisions per second made by the gas molecules with the wall of the container, and the same concept is used to explain diffusion and effusion. Very simple way. Suppose that if we make a hole here we can make a hole. So I know that here is a hole, you know that here is hole, but gas molecules don't know that here is hole. They will try to collide, and during that collision they will come out, right? So this is called effusion. So if you make a hole here, and this through hole gas molecules may coming out, and this is called effusion. So effusion is the release of gas from a very small pinhole. So this is called effusion. And what is diffusion? Diffusion is basically release of gas or mixing of two gases through large surface area. So if you open this one partition and make other gas in contact with this, and when both the gases are mixing through large surface area, that is called diffusion, right? Okay, good. Now see, this is a container. We can say transparent container is this. Molecules are colliding with uniformly with different walls, and here this is vacuum, and see this molecule which is coming to collide with the wall, but here due to hole molecules are coming out. So release of gas molecules through a small spin hole, that is known as effusion. So effusion is basically release of gas molecules through a small pinhole into vacuum. Into vacuum is called is known as diffusion. Diffusion, right? And diffusion is basically more general term than effusion. In diffusion, there is no need of vacuum. Mixing of two gases is called diffusion. So diffusion is basically mixing of two gases. Mixing of two or more gases, simply gases. Mixing of gases through a large surface area is called diffusion. So simply you can say mixing of gases is called diffusion. So here we are, formulating the formula for effusion, and that can also you can use for diffusion. So the rate of diffusion, we can say here, the rate of effusion is equal to ZW, and this is equal to 1 by 4 N by V and A. Right. This is important relation. So this is the rate of effusion. So the collision rate is also known as diffusion. So this is the application of this kinetic theory of gases, one of the application. Okay, so now at constant T, at constant T and P, if T and P are constants, then the rate of diffusion is equal to 1 by 4 N by V, and oh sorry, I have written here bar square. So you average, or this, if we can use this you average. Okay, now it is okay. You average, we can write here 8 RT by pi m, or 1 by 2 into A, right? So this is equation 2. At constant T and P for given gas, right? We can write here rate is directly proportional to 1 by or directly proportional to 1 by root of D. These two relations are known as Graham's law. Right? Means the rate of effusion is inversely proportional to the molar mass or square root of molar mass or square root of density if T and P are constant and for a given gas, right? So, and N by V is the number density. This is also fixed, I mean constant, right? Number of molecules are also constant. So, number of molecules are constant. A means for a given experiment. In a given experiment, the area of the hole is also constant. Molar, I mean pi constant, 8 constant, R constant, T constant. The volume of container is constant. Number of molecules taken constant. So this you can say, rate is inversely proportional to square root of m. But I would like to make one correction here. Rate, this is not the constant rate, but this is initial rate, right? So initial rate of effusion, and basically we try to calculate initial rate, although it is written simply rate, but actually we are calculating the initial rate, because once the gas molecule will coming out, number of moles will change. So this formula is, you cannot say that, okay, you can assume, but practically it is perfectly valid for initial rate. So we can say rate 1 for different gases. We can compare the rate 1 and rate 2 for different gases. We can write here root of m2 by m1 or root of d2 by d1. So this formula you can use for different gases. For different gases, right? So excuse me. This is Graham's law. So now you can define Graham's law at a given temperature and pressure for a given gas. The rate is rate of effusion, or initial rate of effusion is inversely proportional to the square root of molar mass, right? Or square root of density. So the rate of effusion is inversely proportional to the square root of molar mass or density of gas at given temperature and pressure. Right? For different cases, we can compare by using this formula. Now, see, see Now we can express rate in terms of different properties or different units. So units of rate, we can say units of rate. First, in terms of volume. In terms of volume. So we can write here R1 is equal to V1 by T and R2 is equal to V2 by T. This is the rate for the same time. Same time. If time is also variable, right? If it is given in the question, then you can take R1 is equal to V1 by T1 and rate of effusion for gas 2 is equal to V2 by T2. So this is the in terms of volume for different time. For different time, right? So this is for same time, this is for different time. So you can change here in the left hand side R1 by R2 in terms of volume. Clear to everybody? Good. And right hand side is same, under root M2 by M1, right? Now second one in terms of moles of gas effuse out. Effuse out. So in terms of moles of gas effused out, this is the in terms of volume of gas effused out. Effused out, right? So moles of gas effused out for same time if you want. So you can write R1 is equal to N1 by T and R2 is equal to N2 by T. What is this is for same time. So I am taking same time formula I am making here for same time, and if time is different then you can put here different time. N1 are the moles of gas effused out. Moles of gas effused out for gas 1 or of gas 1. In the same time, in the same time, N2 are the moles of gas 2 effuse out, right? They are N2. So this is in terms of moles. So what is the formula? If we take same time, so we can write here N1 by N2 is equal to root of N2 by N1. Okay, dear students, hopefully it is clear to all of you. This is the moles of gas 1 effused out, this is the moles of gas 2 effused out. Okay, now see, suppose that if it is asked, okay, tell the relation, the mass of gas effused out. So B, this is the part of B, this is not independent part. You cannot directly equate mass. because this is very important point. We cannot directly relate this mass of gas effused out with the molar mass, right? Remember, you can relate moles but cannot directly relate mass. You have to convert this moles into mass. So I'm not taking that different case. I'm explaining that in the same case. So mass of gas 1 diffused out, if you want to relation, mass of gas 1 diffused out, diffused out is equal to n1 m1 moles of gas 1 effused out into molar mass, because we do not have any equation in which directly we can relate the mass, right? So we always if you want to convert find out the mass, then you have to convert moles. This is the important point of chemistry. Similarly, mass of gas 2 effused out, gas 2 effused out is equal to N2 N2. Let it is W1 and this is W2, right? So you can write here N1. In place of N1 you can write W1 by M1. So from this equation you can write W1 by M1 by W2 by M2 is equal to root of M2 by M1. So rearrange this equation. So you will get W1 by W2 is equal to M1 by M2 into M2 to the power 1 by 2 by M1 to the power 1 by 2. So this is equal to, we can write here root of M1 by M2. See, many people are doing mistake here. This is important relation. Important relation. What is this W1? W1 is the mass of gas 1 effused out in the same time, mass of gas 2 effused out W2. So W1 is the mass of gas 1 effused out, and in the same time W2 is the mass of gas 2 effused out. So this is in terms of moles, in terms of volume of gas effused out, in terms of mass of gas effused out. Now third is C part is distance traveled by the gas. Distance traveled by the gas, right? So suppose that if we have a uniform cylinder, at the same time we are introducing HCl gas from here and ammonia from here at the same time, gas, HCl gas, Then it is asked that find the distance at which this white precipitate of NH4Cl is formed. So suppose that this is a NH4Cl, because you know HCl and ammonia will react with each other and they will form the white precipitate of ammonium chloride. So ammonium chloride precipitate is let's appearing here. So this is what, let the length is unit here 1 meter or centimeter, whatever you want unit, you can choose your unit. Suppose that this is the distance x, so this is 1 minus x, right? So in the same time, at the same time, if they are introduced here and this is from here, so you can by applying this Graham's law, you can calculate this x, assuming ideal behavior, right? See, uh, rate of motion, you can say rate of movement, or of HCl is equal to, you can write distance traveled by HCl divided by time, x by t, where x is the distance traveled by the HCl. Similarly, rate of effusion or movement, rate of movement of ammonia is equal to 1 minus x by t. This 1 minus x is the distance traveled by the ammonia. So this you can compare with their molar masses or densities if given. So the distance traveled by HCl or per unit time, x by t, x by t by 1 minus x by t is equal to molar mass of ammonia by molar mass of HCl. So you can calculate the value of x, right? You can calculate the value of x. Okay. So in this way you can calculate, but you can use Graham's law of effusion for calculating the distance traveled by the gas per unit time. So in terms of distance also you can put this rate, right? So this is the, all these cases are the cases of simple effusion. This is the case of simple effusion. So it is very much clear that this ammonia is lighter gas, low molecular weight compared to HCl. So this will travel more distance compared to the HCl. That's why I have shown here directly. But you can calculate by using this equation, this x and this 1 minus x. Okay. Hopefully it is clear to all of you, right? Now see another case of effusion, that is known as simultaneous effusion. Simultaneous effusion. So see, simultaneous effusion means when you have taken this two gases together, suppose that we have here suppose that here this is helium and another gas I have taken simultaneously here, some other gas, let it be hydrogen, right? uh, See, so this time suppose that here we have made a hole in the wall here suppose that there is a hole. So now you will observe that you may find a hydrogen molecule may be coming out from here. Hydrogen molecule is moving out, or helium molecule, and some hydrogen molecule also be coming out. So this is, if this situation arises, this is hydrogen, and this is helium which is coming out. So how to explain this? I mean, apply this Graham's law, and what is the, I mean, formula for this? So this time, dear students, the rate of effusion, I mean, the rate of effusion, rate of effusion is directly proportional to number density as well, and square root of molar mass. Now the dependency is like this. See, this will depends that which gas molecules you have taken more, and second factor is the molar mass. So this time you cannot say that hydrogen and helium both will eliminate with the same rate, because both have different molar mass. But molar mass is not the only deciding factor here. Number density also. If you suppose that helium has molar mass 4, hydrogen has molar mass, average molar mass 2. So I mean, so every time in every composition of hydrogen and helium, we will get hydrogen molecule is coming out more. No, you cannot say like this. Okay, lighter molecule have more, I mean, collision frequency. They collide with a more faster rate, but that is not the only factor. This time, their relative population, means number density, also important. Although volume is same for both the gases, so we can say volume is same, but number of moles are different. This time number of molecules are different. So this time your formula becomes, I mean, different. So simultaneous effusion, in case of simultaneous effusion, we have two variables on which the rate depends. So in this case, we have two variables, although T and P is constant, right? No problem. Temperature, pressure is constant. But this time, this rate of effusion, this depends on two factors. First is the number of molecules, molecules, basically number density, you can say, and second factor is molar mass, molar mass, right? So this time rate is equal to, rate is directly proportional to n1 rate for gas 1 n1, or we can see here helium rate, for helium, rate of effusion for helium is equal to moles of molecules of helium, and root of 1 by molar mass of helium, right? And rate of hydrogen, rate of hydrogen is directly proportional to molecules of hydrogen, right? Okay. So you can write rate for helium by rate for hydrogen. This is equal to molecules of helium by molecules of hydrogen, molar mass of hydrogen by molar mass of helium. Okay, so this is the general formula, and now you can transform this formula in terms of some more general term, like this ratio moles of helium by moles of this hydrogen or molecules. This is equal to the ratio of moles of helium by moles of hydrogen. At any moment of time, the ratio of molecules is always equal to the ratio of moles, and ratio of this moles is equal to, you can write mole fraction, ratio of mole fraction of helium by mole fraction of hydrogen. Very simple. And ratio of mole fraction is equal to, you can write partial pressure of helium by partial pressure of hydrogen. What is the problem? So all these terms are equivalent, are equal. So the rate, simultaneous rate of effusion of helium by rate of hydrogen is equal to, you can write partial pressure of helium by partial pressure of hydrogen into molar mass of hydrogen by molar mass of helium to the power 1 by 2. Right? So this is the, formula for simultaneous diffusion, and you can write in any term, right? Either in terms of molecules, either in terms of moles, either in terms of mole fraction, either in terms of partial pressure. Okay, all are equal. So this is the case of simultaneous effusion, and if you have taken this, this is not the effused out. In the left hand side, whatsoever you have written, that is the effused out. So R you can replace in terms of moles, in terms of molecules, in terms of volume, in terms of mass. Here this is the right hand side which is taken in the container. So this is the moles taken. So here in the left hand side you can replace this R in terms of this moles coming out or mole fraction coming out. So sometimes students are confused that what is this mole fraction ratio or pressure ratio, and what is here. Here what is coming out and what is this? This is what we have taken. So you should clear that what the ratio you have taken two or more gases together and what the mixture of gases coming out. So this I have shown you here for two gases. Similarly, three gases may be there. So how to apply this Graham's law for three gases comparison? So you can make two equations, one is to 1 and 2, and if three gases are there, so you can make different equations, 1 and 2 together, 2 and 3 together, and 1 and 3 together. So you can make three different equations, and you can solve the problem, right? So this is the concept of simultaneous effusion, and this is very, very important. Sometimes students are confused from where this pressure is coming. So you can, if you are clear that this number density, so number density is equal to, you can write P into Na by RT, and R and T are constant, and Avogadro's constant is constant. So here definitely that is pressure. And if you are applying that equation in a mixture of gases, then that pressure is called partial pressure. So hopefully all of you are clear what is the meaning of simultaneous effusion. Very simple it is. When you have taken two or more gases together and they are coming out simultaneously, both the gases were coming out, but not in the equal ratio, not in the equal molar ratio they are coming out. So in what ratio initially they will come out, you can calculate by using Graham's law, right? See, one more technical term we are using here, that is enrichment factor. See, enrichment factor, this term basically used in the enrichment of uranium, as all of you are knowing that uranium has two isotopes, major isotopes, 235 and 238. And 235, it is what good fuel, we can say, and its natural abundance is very, very low. Uranium 238, it is more than 99% in the nature, and in atom bomb, the best fuel is 235. So how to differentiate, how to recover this uranium 235 from the mixture of 235 and 238? This this term is used, enrichment factor. So by applying Graham's law and automated system, I mean, many times we are performing the same experiment, same experiment. See here, I have shown here three chambers. First, we what uranium 235, 235 and uranium 238, both were solid. So first we convert this into the gaseous substance. So on fluorination, you will get UF6 235 and UF6 238, both are gaseous, right? So first we convert this uranium 238 and uranium 235 into the gas on reaction with fluorine gas. Okay, and apply this Graham's law many times. So 235 UF6 235, this is lower molar mass, this is higher molar mass. So in the first slot, when you open this, I mean opening, then little bit more molecules of UF635 will come out, because this is lighter and lighter gas have more rate of effusion. So more molecule will come here, less molecule of 238. Then again open the second opening and third and so on. If you keep on doing, then ultimately you will get this 235. So I think in the nature 235 is 0.7%, and if I'm not wrong, then from 0.7% to 7%, if you want to enrich this uranium 235, then you have to perform 512 times of this experiment. So 235 and 238 can be separated by using this Graham's law, and here we are using this enrichment factor. So for the two different gases, the rate of diffusion RA by RB, rate of diffusion of gas B, is equal to NA by NB and MB by MA power 1 by 2, right? This is the equation for simultaneous effusion, because here you will have this simultaneous effusion, case of simultaneous effusion. So here this term MB by MA to the power 1 by 2, this ratio is called enrichment factor. This ratio is called enrichment factor for gas A, right? So enrichment factor for gas A, right? MB by MA. And you know, I mean, the molar mass of A should be less than molar mass of, right? So if molar mass of A is less than molar mass of B, then MB by MA, this is the root, it's called enrichment factor for gas A. Means gas A will enrich here, further it will enrich and further enrich, right? So this is the enrichment factor for the lighter gas, right? So suppose that if you want to calculate the enrichment factor for uranium, so what is the enrichment factor for uranium? Example, calculate the enrichment factor enrichment factor for uranium. So uranium 235, right? This is lighter isotope. So first you have to find the molar mass of UF6 235. So this is equal to 235 plus 6 into 19. So this is equal to 349 grams per mole. Similarly, molar mass of UF6 238 is equal to 238 plus 6 into 19. So this is 352 grams per mole, right? So the enrichment factor is equal to UF6 238 by molar mass of UF6 235 1 by 2. So this is equal to 352 by 349. So this is equal to 1.0043. So basically UF635 is 1.0043 times more effusible compared to the 238. So in this way we can calculate the enrichment factor. And if you know the enrichment factor, then by using this equation you can calculate how many times do the experiment can repeat, so that we can change the percentage from this to that, like that questions can be asked. So in the next lecture I will discuss some questions.